Welcome students. In today's class, we will go through another application of backtracking. The problem here is the sum of subset. Okay. Now, the definition of a sum of subset is given here. In the sum of subset, we will be having a set of positive integers. Positive integers, we can consider them to be weights because we are talking about the backtracking where we are going to use a state space tree drawing. In that there will be certain nodes. The nodes will be connected through the edges. Those edges can have the values, right? So the positive numbers will be given, and what we will try to do is that in that particular subset, we will try to make certain combinations whose sum will become one particular defined value that we can call it to be a M. For an example here, consider this particular set. The set S has 4 distinct numbers. Whatever the numbers in the set we have, those numbers should be different. Those should be distinct. There cannot be any duplicate numbers. Okay. Then next is that now here we are also given with one more value called as the sum, that is 8. What we need to do is here is that we need to find out what are the different values here. If we add them, then the sum is, or the result is going to be the M value. For instance here, if you can look at, if I add 1, 5 and 2, then the sum is going to be 8. Then I can say that one of the subset here, I can denote it as a subset S1. This S1, I can have 1, 5 and 2. If I have these values, then the sum is going to be, whatever the total sum I obtain, that sum is going to be 8. That is nothing but equal to the given value of a M. Then this subset S1 is one of the solution that we can derive using this particular subset, in this particular set. In the same way, can you tell me, will there exist any other possible values, or will there be any possible subset whose sum is going to be 8? If you consider any other 2 distinct numbers here, 2 or 3, any sub values of this one, if you add them, then it should result in a total sum value as 8. Are there any subsets possible here?
Yes, sir.
What
7 and 1.
7 and 1. So I can write one more subset here saying to be S2 equal to 1, 7. Then this is another subset whose sum is going to be 8. That is nothing but the given value M. So this sounds very simple to calculate, right? If there are any number of if there are n number of distinct positive numbers in a set, then we can manually try to count how many possible subsets we can derive at whose sum is going to be the M value. But this type of problems can be very easily solved using the backtracking concept. Okay. Now let us try to understand how we can have, or how we can solve this type of problems using the backtracking. We know that in the backtracking, we make use of space, that is state space tree, right? Yesterday in Hamiltonian cycle, we have seen how we can draw the state space tree for a given graph. Let us try to understand and try to draw the state space tree for this sum of subset problem. Pay attention, it is little tricky to understand. It is simple, but it is tricky to understand how we draw the child. Okay, now assume that right now when we begin with when we are trying to draw the root node, okay, the value is going to be 0. The root node will contain a value as 0 here. Why 0? Because for when we start deriving the total sums, that is the subsets, right now we have not considered any of these distinct integers, right? Now it is 0. What I can do now, from 0, now I can consider the first number, that is 1. I can consider, or I need not to consider. If I consider it, then I will go along with the left child of the root node. If I consider the first number, if I don't consider, then I will go along with the right child of a particular node. Right? Already we know that one particular node can have one or more children. Here, when trying to look upon the binary tree, in case of binary tree, one particular node can have maximum of 2 different children. Now, how we are going to deal with the children, or how we are going to draw the children, is basically whether we are going to consider a particular number in the set. If yes, then we will draw it along the left child. If we are not considering, then we will draw it along the right child. For an example here, since at the beginning I don't have any value, I have not selected any value, so the total sum is actually 0. Now, suppose if I think that now I'm going to select the first integer, that is the first number in the set, then what I would do is that I would draw one particular left child from the given node, and I will say that I'm going to consider the first digit or the first integer over here. When I say that I'm considering it, I will draw, or I will write the edge value as whatever the value of this particular integer is. The integer value is 1, and since I'm considering, I will denote it as +1. +1 here indicates that, okay, I'm considering the first integer here. When I consider the first integer, then my sum is going to be what? The previous value is 0, and then if I consider 1, then the sum is going to be 0 plus 1, that I get it as 1. So the root node, the node value indicates the total sum, and the edge value indicates whether we are considering that particular integer or not. If we are considering, then we will denote it as +1. And once we derive at the child, then the child node, whatever comes, the value, that value is going to be the total sum from its previous. Is this understood, the first step? Please do acknowledge if it is understood or not.
Yes, sir.
Fine. Okay. Now, the set values, the first number I have considered, I have taken it in my calculation of subset. What we have in the next value is 5. Now again, I have got two possibilities. I can either consider 5 or I need not to consider 5. Now I want to find, if I consider, what will happen. So what I will do, from root, that is from the node 1, since I'm going to consider 5, I will draw one more left child, because left child will indicate that I'm going to consider the value. Which value I'm going to consider here? I'm going to consider the value that is 5. That means the edge value will be +5, correct? Then the node value, the child which I have derived now, this particular node value is going to be whatever the previous value I have, in that I'm considering 5 and then I am deriving at. So it is going to be 1 plus 5, that will give me a value as 6. Is this step understood, how we derived at the value 6 for this particular child?
Yes, sir.
Okay. Now, so in the given list, 1 is considered, 5 is considered. The next value what I have is 2. Now, whether I can consider 2 or not, that I need to check. Now, the current sum at this stage, the current sum is 6. And in this 6, if I consider 2, I'm going to get the value as 8. Is that 8 value, is it greater than the given sum value m? I need to verify. If it is not greater, then only I can select. If it is greater, then I should not select it. In this case, the current sum is 6 and the next value is 2. Yes, that means what? I can consider this 2 in the next derivation. So in the next derivation, I will draw one more child from the 6, and that corresponding edge value, I will represent it as plus 2. Plus 2 because now I'm going to consider 2 and I will add it into my subset. And when I add 2, then the total value in this particular node will be the previous sum plus 2, that I get it as 8 here. Okay, now look at the node value here. Is this the what actual sum we are looking for? Yes, the m value is 8, and here we have derived the node value to be 8. That means whatever path I have traveled from the root node up to this particular leaf node, if I go in this particular order, then I get one particular solution. That solution is what? The sum of subset, which produces the sum as 8. What are the values I need to consider? I need to consider 1, I need to consider 5, and I need to consider 2. That will give me the first subset. So the subset S1 is going to be I considered 1, I considered 5, and then I considered 2, and that gave me the total sum as 8. Is this flow understood?
Yes, sir.
Okay. Now, once we get a solution, that doesn't mean that there will not be any other solutions. There might exist few more solutions. How we can come to know? By drawing complete state space tree. So in order to now do the backtracking operation, suppose at 8, now you might be thinking there is one more number existing here in the given set, 7, right? If I consider 7 to 8, if I add into 8, then definitely it will become greater than our final value, that is m value. So I should not consider it, right? So now what I should do? I should backtrack. Backtrack means what? From 8, now I'm backtracking to its parent. The parent is what? This particular node 6. Okay, now pay attention and try to understand this particular step very clearly. From 6, we navigated towards the left side by considering 2. Then I have got one more operation here, that if I don't consider 2, then what I will arrive at? That is the right child of 6. If I don't consider 2, then the corresponding edge value, I'm going to denote it as -2. Pay attention here. This is the tricky part. Okay. From 6, if I consider 2, then I will denote it to be a +2, and then I know that I have to drop in the left child. If I don't consider the 2, then I need to denote it by the edge value as -2. Okay. But what will be the node value that I need to have it here? That is important. Previous value is 6. Previous value is 6. And if I don't consider 2, here minus means I don't consider 2, then what will be the total sum? Can you answer? Will it be 6 or will it be something different? The previous value, the sum is 6, right? That is 1 plus 5. I got a 6. And then if the next number is 2, and now I'm thinking that now I am not supposed to take this particular 2 in my subset. If I don't consider this 2, then what will be the total sum at that particular point? Is it 6 itself or it is different?
6 itself.
It is 6 itself. Why I said it is tricky, because you may think here 6 plus 2 is 8, then 6 minus 2 is 6 only. You might be thinking, how come, sir, it is 6 minus 2 is 6, 6 minus 2 is 4. But you need to think here is that we are not subtracting any value here. This plus and minus symbol indicates that whether we are considering that particular integer value or not. Minus indicates means we are not considering that particular value. Previously, there was a, you can think something like that. In front of you, you have given with certain money. Okay, assume that you have certain money. It is asked whether to pick those particular currency or not. So you may think that, okay, you want to make a 8 rupees. Assume that there is a 7 rupees coin also exists. Okay, then you will take 1 rupee coin. Then you will plus 5 means you will take 5 rupee coin. So that will make you 6 rupees. Right? Then from 6 rupees, suppose if you don't want to take 7, if you don't want to take 2, if you don't take 2, then also whatever you have collected that time will be 6 itself. That's why the right node will be having the same value as its parent value. The right node of any particular parent in a sum of subset will have the same value as of that. Understood?
Yes, sir.
Now I am at the node number 6, and in my list, in my subs, in the set, 1 I have taken, 5 I have taken, 2 I did not take. The next number is what? 7. Now, what do you think? Should I consider 7 here? If I consider, then what will happen? 6 plus 7 will happen. So 6 plus 7 means I get a sum as 13. Is that 13 greater than our m value? If I consider 7, it is going to be 6 plus 7, right? Is it greater than our m value? Definitely, right? The m is actually what? It is 8. So it is going to be greater than m. If I consider 7, then that means that I will not get the solution, because the total sum of that subset is going to be greater than the total sum which we have given with. That means if I go with this particular route, I will not get any solution. That means it is a dead end. So that dead end is highlighted in the node. Understood?
Yes, sir.
Okay. Now as a general concept of backtracking, now we know once we reach a dead end, what has to be done? Backtrack. Backtrack means where? From 6 go to its parent. That means we come at this particular node 6 here. Now there are no other possibilities downwards. Then what we need to do? Again, we need to go upwards. That is backtrack. Backtrack means now I will go to the parent of 6. The parent of 6 is the root. Sorry, not the root. The node 1. When I am at node 1, that means what? I have only considered first number in my subset. Okay. Now what we need to do? We need to draw the right child of this particular node. So right child of this particular node will be what? Can anyone tell me what should I write the edge value here from 1 towards its right child, and what value I have to write within this particular right child node?
-5.
-5, correct. Good. What will be the value of this right child node now?
1.
1. Very good. That means I did not consider 5 in my subset. So the total sum is going to be whatever the previous sum I have. Okay. Now I am at here. What I did? 1 I selected, 5 I did not select. Then what is the next number? Next number is 2. Now I can consider 2 or I need not to consider 2. Now let us go with the value when I consider the 2 in my subset. So I need to draw a left child. Since I'm considering that particular number, that has to be drawn on the left side of that particular parent. That indicates I'm considering the next number, that is plus 2. So if I consider plus 2, then the total sum is going to be the previous sum, that is 1 plus 2, that I get it as 3 here. Okay. Now I consider 2. The next number is what? 7. Now, tell me, should I consider 7 now? From 3, if I go downwards, means if I want to draw a left child, that means I should consider 7. So what will happen? 3 plus 7, it is going to be greater than the m value. That m value is 8. What it means? Is it a valid option or it is an invalid option?
Invalid.
Invalid. That means I should not consider 7 here. Means this is a dead end. So draw a dead end signal for this particular node. Since there is a dead end, that means now I have to go backtrack. So I need to go back now. So from 3, I will come back to 1. And now I know that since I don't want to consider 2, then I will have to draw a right child. And in that particular right child, the value is going to be the same as its parent. So here it will be -2. It will be -2, and the sum is going to be 1 itself. 1 itself. Now, if you look at this graph where 0, 1, and then 1, and then this one, what we have done? We have chosen 1. We did not take 5. We did not take 2. Then I am left out with the last number, that is 7. I may consider 7. I may not consider 7. What will happen if I consider 7? Let us check it out. Now, I'm drawing a left child. Now, the left child, if I consider it, then I need to do the plus number with that one. So I get the edge value as plus 7. Then the total sum is going to be 8 here. Now, will I get a proper solution if I go in this particular order? Yes, because the total sum, what I have here, it is exactly equal to the given in the problem, that is m value. So in order to get this one, what are the values I have selected? I selected 1, then I selected 7. That means the second subset here, what I have derived is as 1, 7. Understood?
Yes, sir.
Okay. Now I need to figure out whether does exist any other solutions. So how I can do? Backtrack. So from 8, I will go to the 1. There are no other options. There are no other numbers. So I will go back to its parent. So I will come at here. Then I will come at again to the 1. Then I will proceed with the further steps. Is that followed, student? Are you getting this state space tree drawing?
Yes, sir.
Just a moment, students. Let me try to show you one more screen. Now, what we have seen is that we started from 0th node, and in the given set, we had 1, 5, 2, 7. So 1 was the first number or the element in the set. So we considered 1, that is including 1, we traversed on the left child of 0. Now what we can do is that we can draw the right child from 0th node, wherein we will not include the first number, that is 1, in the subset. We will exclude this 1 from the subset, and then we will keep on drawing the right child tree of 0. And in this one, already we have seen that whenever we don't include any numbers, we will represent the corresponding edge by a negative sign with respect to that particular number. Okay, and then we will keep on adding the node values with whether we have considered that number or not. So if I go further drawing the right child tree of the 0th node, we may end up something like this. Okay, now let me briefly just go through this one, how I have derived the right child tree of a 0. Now, pay attention here. The first number or the first element is 1, so I will not consider 1 in calculating the subsets. So if I don't include means I need to include it by minus. Okay, I need to represent the edge by minus sign. Okay, now if I don't include means 0, in my 0 I'm not going to add any number, so the sum is going to be 0 itself. It will be retained as 0 itself. Okay, and the corresponding edge will be minus 1. That indicates that, okay, in the list I have not included 1, but I will decide gradually whether to include the next numbers or not in the next levels. So in the next levels, what I can do now, I will be at this particular node, that is 0, this particular node, and here the next number is 5. So now I have got two possibilities. One is that I can include 5 or I may not include 5. If I want to include, then I need to go with the drawing again a child from the 0th node here with on the left side. Okay, so 0 plus 5 is going to be 5. So this 0 and 5 I will draw, and the corresponding edge I will denote it as plus 5. That indicates that, okay, now I'm including 5 in calculating the subset. Okay, now after I reach to this node, then the next number available with me is 2. Now again here I have got two possibilities. I can include or I may not include. I will include it and I will go further. So from here I will draw one more sub-child on the left side including 2. So that is plus 2. So 5 plus 2 is going to be 7. Okay, now after here the next number is going to be 7. Okay, now see here what will happen. Now I am at this particular child node, that is 7. If I want to include this 7, then the next left child of the 7 is going to be 7 plus 7, that is 14. But that 14 is greater than the m value that is given in this particular problem. We should not, the left child, the value of the left child node or any node cannot be greater than the total sum that we need to calculate. But in this case, what will happen if I go further, including this the last number 7 on this particular child tree, then I may get the total sum as 7 plus 7, that is 14, right? So that becomes the dead end here. I cannot include it. So here dead end will come. So I need to mark it as dead end. So now once I get a dead end, then backtrack. As the concept says, backtrack. Backtrack means how I derived this particular child. I derived this particular child from its parent, that is 5, where I included 2. Now what can I do? I will not include 2 in drawing the next child. That is, I will go back to 5 and I will not include 2. Then I will proceed further with the right child tree. By this time, you might have noticed that whenever we are not including the values, right, we are representing anyway it by the negative sign. At the same time, the right child node, the value is going to be the same as its parent. Okay, now I did not include 2. The next number is 7 in the list. So if I wish to include 7, what may happen? 5 plus 7, that is going to be 12. Again, that 12 is greater than our m value, that is 8. That means I cannot include 7 as well. So it implies that again, this particular getting the solution in this order will also reach us to a dead end. So we will not get any solution in this order also. Since we don't get, so backtrack. So backtrack means again go back to 5. Now again here from this one, we have tried out all the possibility from this particular node and we have reached to a dead end here. So come back to its previous node, that is 0th node. So this particular 0th node on the next level, this level indicates that we have not considered 1, and we tried to look into one more variation where we considered 5 and we reached the dead end. So next possibility is that I will not consider 5 in my subset. So I will go along with the negative sign. So by drawing a right child from 0. So here the edge will be indicated as -5. That means I did not include -5. So this particular node 0 on this level, third level, indicates that I'm in a path where I did not include 1, I did not include 5. The remaining elements in the set are 2 and 7. Now I need to figure out whether will there exist any subset that will give the total sum as the value 8. Okay, the next element here is 2. So now here I will try to include 2. If I want to include 2 means I need to draw a child on the right hand side, on the left hand side. So from 2, from this particular node 0, I will arrive at one more node 2 with +2. So that indicates I am including 2 in the subset. The next element is going to be the 7. If I wish to include, then the next left child of this particular 2 is going to have the value as 2 plus 7, is going to have value as 2 plus 7. But what will happen? The 2 plus 7, the value is going to be 9, that is greater than the 8 value. That means this 2 is also a dead end. We will not get the solution. Now we need to again go back. That is backtrack to the previous node, that is parent. Now here I included 2. Now I will proceed with not including 2. Okay, that means I will have to draw a right child. Okay, in this right child, the value is going to be same as the parent itself, but with a negative sign, -2. Okay, now this particular 0 on the fourth level, what it indicates is that I'm in a verge of calculating the sum of subset where I don't want to include 2, that is first number -1. I don't want to include 1. I don't want to include 5. And even I don't want to include 2. And let me try to figure out with the only one number that I have in the list. The number that I have in the list is 7. So let me try that. Let me include 7 in the subset. So I will draw a left child. Okay, and left child, when I draw, I get the value as 7, and corresponding edge will be +7. And if you notice that there are no more values present in the, or no more elements present in the given set, and we did not get the proper value. The total sum is not here as 8. That means again this is a dead end. So once we get a dead end, again go back, that is backtrack. So next time we will try to draw a right child from this 0th node by not including 7. So we get the value as 0 itself. And at this stage, we have reached to the end of the list in the given set, and we did not select any elements, and we got again a dead end. So once we get a dead end, come back, backtrack here, backtrack, and come back to the initial node. Okay, now this entire graph, or this entire tree that we have drawn here gives us the state space tree. Okay, wherein we try to figure out the sum of the subsets that whose value is going to be 8. The m value here was given as 8. So what we figured out was, by drawing this state space tree, there are two different possibilities in which we can get the proper subsets. The first one is that in the subset we can include 1, we can include 5, and we can include 2. So if we include these 3 values, then the total sum is going to be 8. So our subset 1 is 1, 5, and 2. The second subset is that we include 1, we will not include 5 and 2, but we will include 7. That means 1 and 7 will give the value as 8, that is sum as 8. So this is the second solution what we can arrive by drawing the state space tree here. For the point of examination, students, if a question comes for a 5 marks, then drawing this space, that is state space tree, will carry 4 marks, and writing the final answer, that is subsets, carries only 1 mark. So the drawing state space tree with the proper values is very important. I hope you understood the concept here. In the similar way, you can try to solve one more example based upon the sum of subsets. The given set elements are 6, 8, 2, and 14, and the sum, that is m, is going to be 16. So you need to draw the state space tree starting node as 0. Then you may start with the left child as +6, and then you can go with a +8 again further down until you get a 16 values, and try to find out how many possible subsets we can derive at here. If you just glance through this number, then the possible values going to be 2 solutions here. So try to find out those 2 solutions and get the answers. Okay.